Good morning. I'm very glad to speak with young people because the topic that I want to speak on is not only a scientific issue, but it is a moral issue, and particularly it involves the issue of intergenerational injustice, where the present generation is burning the fossil fuels and causing a climate change, but it is young people and future generations which will bear the consequences of that. And I will also argue that it's also a legal issue, which we should be suing our governments to do their job. The status of the global warming climate change issue is that there is a large gap between what is understood by the relevant scientific community and what is known by the people who need to know, and that's the public. The truth is that we have an emergency. We have a crisis, but that is not obvious because the climate system has great inertia. The ocean is 4 kilometers deep. The ice sheets on Antarctica and Greenland are 2 or 3 kilometers thick. They do not respond quickly when humans begin to cause climate forcings that can cause change. But that inertia is not our friend, because once changes begin to occur, they become very difficult to stop because of the momentum of the system. There's the danger that we can push the climate system beyond tipping points, and the dynamics of the system can begin to take over, and the changes will occur more rapidly and out of our control. For example, if an ice sheet begins to disintegrate, it is sliding down the slopes to the ocean, then it's too late at that point. You can't tie a rope around the ice sheet or build a wall around an ice sheet which is 2 kilometers thick. The bad news is that what's become clear is that the safe level of atmospheric carbon dioxide is actually much lower than what we thought even a few years ago. The good news is that it's still possible to solve the problem, but only if we begin to take actions very quickly. Now, to say a few words about climate tipping points. Well, I mentioned ice sheets. The principal process there is the ocean begins to get warmer, and the tongues of ice, the ice shelves which come out from the major ice sheets and go into the ocean, as those begin to melt, because those buttress the ice sheets, once the ice shelves are gone, then the ice sheets can expel large icebergs to the ocean much more rapidly, and the ice sheets can begin to disintegrate. It's already been mentioned that one of the other phenomena that we're especially concerned about is species extermination. Because the rate of global warming, if you average over 10 years, we see that a given temperature line is moving poleward at a rate of about 50 to 60 kilometers per decade. Some species, as this migration, as the climate zones shift further, some species can migrate and stay within a climate zone in which they can survive. But some species cannot migrate so rapidly, and that can cause some species to go extinct. And if some go extinct because they depend upon each other, that can cause ecosystems to begin to collapse. And we know that in both of these cases, in the case of ice sheets and species extermination, we know that these are not just theoretical ideas, because we know from the history of the Earth that there have been cases when ice sheets disintegrate rapidly and sea level goes up at a rate of 1 meter every 20 years for centuries. And we know that there have been times when the planet warmed by 5 or 6 degrees Celsius, and it drove a significant fraction, a large fraction of the species on the planet to extinction. And then, of course, new species evolved over hundreds of thousands and millions of years, but that's a time scale which we can't, humans can't imagine. If we drive species to extinction, it can be a much more desolate planet for any time scale that humans can think about. This was my first grandchild, Sophie. I used this photo when I gave a talk at Lamont Observatory in year 2000 because the day before a newspaper described me as the grandfather of global warming. And that's not true. There have been scientists talking about greenhouse effect since the 1850s. So, but at least I was really a grandfather. You know, it was mentioned that I have become more involved in recent years in public discussions about human-made climate change and what actions we need to be taking. Actually, I tried quite hard to stay out of the public. I had testified to Congress in the United States in the 1980s, and that got quite a bit of attention. And I, at that time, decided I did not want to be involved in the public discussion because I'm not naturally a public speaker. I prefer to do science. My interest in science was that which Richard Feynman has described, the pleasure of finding things out. I like to try to understand the climate system, but I didn't like the public aspect. So whenever I received requests from the media, I would refer them to Steve Schneider, who was a friend of mine and a very articulate scientist who liked to speak to the media, and Michael Oppenheimer, who is also very good at that, until about 5 years ago, when I realized there was this big gap between what was understood by the scientists and what was known by the public. So I decided I was going to give one talk, and an organization said they would sponsor this in Washington and have media. And so I worked for 6 months preparing very carefully the talk and some scientific papers to back up what I was saying. And actually that specific talk got canceled because it was during the election year, and the organization decided they didn't want to risk the anger of the administration. So I had to ask my professor at the University of Iowa to arrange for me to give a talk there. But that one talk, I of course didn't really help reduce this gap. So then I gave a few more talks, and finally I reached a point a few years ago where I said I don't want my grandchildren to say that Opa understood what was happening, but he didn't make it clear. And so I tried a little harder, and I went to several countries and actually had the opportunity to speak to high-level politicians in 6 or 7 different countries. But what I found was that what the governments say, even the governments that I thought were the greenest, that really understood the problem, they say we have a planet in peril, and they say the right words, but if you look at the policies, they're not consistent with that. Even let's say the greenest nation, one of the greenest was Norway. Their local policies are very good, and they try to reduce their local emissions. But the government owns Statoil, which is developing the tar sands in Canada, which is the dirtiest fossil fuel on the planet, and it has the most carbon dioxide emissions. So there's no nation that in fact is dealing with the issue. Well, when I gave my talk at the University of Iowa, still at that time I was just doing the science, and I was using my grandchildren then. By then I had 2 grandchildren, and I was using, Sophie was trying to explain how the greenhouse effect works. The greenhouse gases make the atmosphere more opaque in the infrared region. So the heat radiation from the Earth to space arises from a higher level in the atmosphere if you add more greenhouse gases. And because the temperature is colder as you go to higher levels, that means the emission to space is reduced. And then the planet is out of energy balance because the gases do not affect how much sunlight the Earth absorbs. So you have more energy coming in than you have going out. And we can calculate that very precisely because we know the properties of CO2 and methane. And it means that the planet would be driven by a forcing of 3 watts per meter squared if greenhouse gases were the only thing that changed. That means that over each square meter of the Earth's surface, it would be equivalent to having 3 of these tiny 1-watt Christmas tree bulbs over every square meter. Well, but humans are also doing another thing. We're also introducing air pollution, particles in the atmosphere that scatter sunlight, and that reduces the heating of the Earth by 1 to 2 watts per meter squared. So Sophie was trying to explain that the net effect of humans is a forcing of about 2 watts per meter squared, but Connor could only count 1 watt. And the truth is, because we're not measuring the aerosols as accurately as we should, the actual forcing could be someplace between 1 watt and 2 watts. But we know our best way of confirming our understanding of the physics is to measure the energy imbalance of the planet. How much does the absorbed energy exceed the heat radiation to space? Where can this energy go? The atmosphere has a very small heat capacity. It's very thin. And the continents have a very low heat conductivity. So only the upper few tens of meters of the ground actually change temperature. The only place that can hold a lot of energy change is the ocean, which mixes, and it's 4 kilometers deep on the average. So we can determine the planet's energy balance by measuring the temperature in the ocean accurately. And what we find, we've begun several years ago to have several thousand floats distributed around the global ocean, and which have an instrument package that yo-yos down into the ocean for 2 kilometers and it yo-yos back up. And it measures the temperature in the ocean very precisely. And what we see is that the heat content of the ocean is increasing. The ocean is becoming warmer. And it implies that the planet is out of balance by about 3/4 of a watt per meter squared. The accuracy is still not perfect, but it's out of balance by at least 1/2 a watt per meter squared. And that's consistent with what we expect, because this energy imbalance has already caused the planet to warm up by about 0.8 of a degree Celsius, with most of that warming occurring in the last 30 years. This is the temperature of the Earth's surface averaged over 5 years, which is 60-month running mean. So we get rid of the noise. There's a lot of fluctuation from year to year just because of the natural variability The atmosphere and ocean are fluids which are sloshing around. The El Nino, La Nina cycle causes year-to-year temperature variations. But if you average over 5 years or average over 11 years to take out the sun's natural variability, then you see that the temperature is going up quite linearly in the last few decades. But that's only about half of the warming that we expect due to this energy imbalance of between 1 and 2 watts, probably 1.5 watts. The other warming is still in the pipeline. That's because the planet is out of balance. It's still going to warm up by this much more, even without any additional changes in greenhouse gases. Now, the basis by which we understand the climate system is especially aided by our studies of the Earth's history, how the Earth's climate responded in the past when there were changes in the boundary conditions, in the atmospheric composition, or in the surface properties of the planet. Also, the last few decades, we've begun to measure changes in the Earth's climate very accurately from satellites. And then finally, there's also climate models and theory, which helps us interpret those observations and the history of the Earth. So to start with a few remarks about the Earth's history, this top graph shows the temperature in the deep ocean over the past 65 million years. On these timescales, there are huge climate changes. Between 65 million years ago and 34 million years ago, the planet was so warm that there were no ice sheets on the planet. There were alligators in Alaska. It was tropical climate at high latitudes. And by the way, the last 5 million years, I've expanded in the middle graph, and so you can see these oscillations in the average temperature of the Earth. Those are the glacial to interglacial swings of the climate. And then I've expanded the last 500,000 years in this bottom graph, which shows in more detail the global temperature oscillations in the past few 100,000 years. Okay, so we have the Holocene is the present climate era that we live in. The last 12,000 years have been very stable climate, a warm interglacial period, and sea level has been very stable. 20,000 years ago, the world was about 5 degrees Celsius colder. There was an ice sheet that covered Canada. There was a smaller ice sheet on northern Europe. Let me first discuss the very large climate changes that occurred over 65 million years. We know the basic cause of these climate changes. They have to be due either to changes in the amount of energy coming into the Earth, or changes within the atmosphere, or changes on the surface of the planet. But we know that the energy coming into the planet has not changed very much. The sun is a normal main sequence star. It's burning hydrogen to make helium by nuclear fusion in the sun's core, which the sun is slowly getting brighter over time. So over 65 million years, it has become about 0.4% brighter, which, because the Earth absorbs 240 watts of energy from the sun, 0.4% is 1 watt per meter squared. we also know that 65 million years ago, the continents were already close to their present latitudes. And so the changes in the surface, the reflectivity of the surface due to the location of the continents was also quite a small effect, a forcing of less than 1 watt per meter squared. But the amount of carbon dioxide in the atmosphere over this time period changed from more than 1,000 parts per million 50 million years ago to as small as 170 parts per million during the ice ages. So that is a change of at least 3 doublings of carbon dioxide, which means a climate forcing of more than 10 watts per meter squared. So the dominant cause of climate change over these long time periods is changes in atmospheric CO2. That's an order of magnitude greater than the other possible causes. And we know why the amount of CO2 changed, because the amount of CO2 in the atmosphere is determined by the balance between the source of CO2, which is volcanoes, and the sink for CO2, which is the weathering process. As the rivers carry sediments to the ocean, the chemical reactions associated with that weathering process deposit carbonates on the ocean floor, and that takes CO2 out of the atmosphere. And those processes do not need to be in balance at any given time, because the amount of volcanic activity depends upon continental drift. The volcanoes occur at the edges of the continent. As a continent moves over the ocean floor and subducts beneath it, ocean floor, the heavy pressure and high temperatures caused by the continent overriding the ocean floor cause a metamorphosis of the ocean floor into rocks such as basalt, and this process releases carbon dioxide, which comes out of the volcanoes and the seltzer springs associated with the edge of the continents. But that depends upon where the continental drift is occurring. The one thing that was very different 65 million years ago was India was still south of the equator, and it was moving north at a rapid rate of about 20 centimeters per year, which is quite rapid for continental drift. And it was going through this ocean, which had long been the depot center for major rivers of the world. So the ocean floor was very carbonate rich, and the CO2 was coming rapidly out of these volcanoes, and that caused the planet to get warmer and warmer until India crashed into Asia. And as India began to push up the Himalaya mountains and the Tibetan plateau, then of course this source of CO2 was reduced, and the weathering of the Himalaya mountains is a sink of CO2, so the CO2 began to decrease and the planet became colder, until it finally became cold enough that you could get ice on Antarctica. And Antarctica then froze over quite rapidly. There are two important conclusions from this. The one is that the natural process can cause a very large climate change, because the difference between the source and sink of CO2 is of the order of 1/10,000th of a part per million per year. And over a million years, that amounts to 100 parts per million of CO2. So that's a very large change. It can cause a big climate change. But if we compare that with what humans are doing, humans are now increasing CO2 in the atmosphere by 2 ppm per year. So humans are now 10,000 times more powerful than the natural geologic changes. So humans now control future climate. The other important conclusion is that the Antarctic ice began to form when CO2 became as small as about 450 ppm. Some other scientists estimate a higher number than that, maybe 600 ppm. But the point is, the present amount of CO2 is 389 ppm. It was 280 ppm when the pre-industrial amount. But because of fossil fuel burning, we've increased it to 389. If we burn all the fossil fuels, it will be at least 800 or more ppm, which would mean we would be heading the planet back to the ice-free state. It's difficult to say exactly how long it would take the ice to melt, but we would certainly be creating a different planet than the one that civilization developed on. I think that the oscillations, the glacial to interglacial oscillations, are also very interesting. But I think I better just summarize briefly and say that these oscillations from warm interglacial periods to ice ages, these are associated with perturbations of the Earth's orbit. Jupiter and Saturn tug on the Earth's orbit, and they slightly perturb the Earth's orbit, which affects the seasonal distribution of sunlight on the planet. So, for example, the tilt of the Earth's spin axis relative to the plane of the Earth's orbit wobbles by plus or minus 1 degree. And when it's tilted more, then there's more sunlight on the high latitudes, and the ice sheets tend to melt. And as ice sheets become smaller, they expose darker surface, and that causes the planet to be a bit warmer. And as the ocean gets warmer, it gives up carbon dioxide, the same way that a Pepsi gives up CO2 if it becomes warm. So in this case, the CO2 is a feedback. It amplifies the climate change that's due to the changes in the orbit. And that's very useful for helping us understand how sensitive the climate is to changes in CO2. In fact, these climate changes from glacial to interglacial are entirely, about 99% of the change is due to the CO2 and methane change. It causes about half of it. And then the albedo change, the reflectivity change of the Earth's surface. Both of those are slow feedbacks that amplify the changes in these solar radiation. But now let me talk about things that are happening to Earth's climate today, which we observe. We began to make satellite observations in the late 1970s. And one of the things we observe is the amount of sea ice in the Arctic. At the end of the summer, this graph shows how much sea ice remains. And it fluctuates from year to year because depending on the weather that summer. But overall, the amount of CO2 is decreasing. It's decreased by about 30%. In fact, this year, the Northwest Passage was open. You could take a ship from the Atlantic to the Pacific because the sea ice was decreased so much from its normal amount. Another thing, and in fact we're going to lose all of that Arctic sea ice within the next few decades if we continue to emit CO2 at the rate that we are now. Another thing that we observe from satellites is the melting of ice on Greenland, the red area. And that area has been, well, it fluctuates from year to year, depending upon the weather, cloudiness, but it's increasing over time. And that meltwater on the surface of Greenland will go to a low spot on the ice sheet, and then it burrows a hole in the ice sheet. It goes all the way to the base of the ice sheet, and it speeds up the discharge of these giant icebergs to the ocean. Still, we didn't know for sure what the effect would be on the mass of the ice sheets and sea level, because as the planet becomes warmer, the atmosphere holds more water vapor. So the snowfall increases. Those places that are cold enough to have snowfall will get more snowfall. And so the ice sheets grow faster at the center of the ice sheets. They melt faster at the edges of the ice sheet. Well, common sense would tell you that as the planet gets warmer, probably the ice sheets are going to get smaller. Now we can measure that very precisely because we have, beginning about 7 years ago, a satellite called a gravity satellite, which measures the gravitational field of the Earth with such a high precision that you can measure the changes in the Greenland and Antarctic ice sheets. And during the winter, the ice sheet gets heavier, and then in the melting season, it loses mass. But overall, it's losing mass. This is the Greenland ice sheet. It's losing mass at more than 200 cubic kilometers per year. And Antarctica is also losing mass at a rate of more than 100 cubic kilometers per year. And what is a bit of concern is the fact that the rate at which they're losing mass seems to be increasing. The record is still very short, but that's the concern that the ice sheets will begin to disintegrate much more rapidly, and sea level will begin to rise more rapidly. Right now, sea level is going up at a rate of 3 centimeters every decade, which is not negligible. We can already see effects on some coastal areas, and some low-latitude islands are beginning to sink into the ocean water. But what we're concerned about is the possibility of much more rapid sea level rise. Another effect of global warming is expansion of the subtropics, the overturning circulation, the rising in the tropics and sinking in the subtropics. That circulation cell is expected to expand as the planet becomes warmer. And we observe empirically that it has, on average, expanded by about 4 degrees of latitude. That's one of the reasons why we see the effect in the southern United States, in the Mediterranean region, in Australia, and other parts in the southern hemisphere. It's one of the reasons that Lake Mead and Lake Powell are only half full now. It's one of the reasons that fires have been increasing in the southern United States, in Greece, in Australia. And these fires burn hotter because of the higher temperature, and that is damaging because it burns not only the trees but the seeds, and so it's more difficult for forests to recover. Another thing that we observe is that glaciers all around the world, in the Rockies, the Andes Mountains, the Alps, the Himalayas, the glaciers are receding. And that's important because some of the major rivers of the world, the Ganges, the Brahmaputra, the Indus rivers, during the dry season, more than half of the water in the river is coming from melting glaciers. Once the glaciers are gone, then you'll get much bigger floods in the spring with the snow melt, but you get much drier rivers in the dry season. And there are actually billions of people who depend upon these rivers for fresh water. Another effect is on coral reefs, which are under stress for several reasons, but 2 of the most important are the increasing ocean temperature, which causes the coral to expel their symbiotic algae and die, and also the acidification of the ocean. As there's more CO2 in the atmosphere, the ocean becomes more acid. And those animals that have a carbonate skeleton or carbonate shell are harmed by the increasing acidity. In fact, that will eventually dissolve carbonate as the ocean becomes more acid. So there are several reasons why we argue that we should try to keep CO2 less than 350 parts per million if we want to keep a planet similar to the one that has existed during the Holocene, the last 12,000 years. The most quantitative way for assessing the CO2 level is looking at the planet's energy imbalance. if we know that the planet is out of balance by at least half a watt per meter squared. If we want to restore that balance by reducing the greenhouse gases, we would have to reduce CO2 by 35 to 40 ppm to increase the radiation to space by half a watt. That means back to at least 350 parts per million, if we want to preserve a planet like the one in which civilization developed. Now, what the implication of that is that we cannot burn all the fossil fuels. What we have burned so far is the purple parts of oil, gas, and coal. There's some uncertainty about how much fossil fuel remains to be in the undiscovered reserves. But we cannot burn all of this coal, and we cannot burn the unconventional fossil fuels. That means tar sands and tar shale, for example. If we phased out coal over the next 20 years linearly, then because of the finite supplies of oil and gas, CO2 would peak at something above 400 parts per million and then begin to slowly decline. It would take a few centuries for it to get back to 350 parts per million as some of the CO2 mixed into the ocean. But we could actually get it back below 350 ppm sooner if we would reforest all the areas that have been deforested. If we'd reforest the areas that are marginal for agricultural purposes. And we could even get it back a little faster if we would start burning biofuels in power plants, capturing the CO2 and sequestering that. But the basic point is that the essential requirement is we must phase out coal emissions promptly, and we cannot burn the unconventional fossil fuels. But what's actually happening? The United States has just signed an agreement with Canada for a pipeline to carry tar sands oil to Texas, oil refineries. And coal-fired power plants are still being built all around the planet, including, I understand, Italy. But so the governments say that they understand we have a problem, but there's a huge gap between their rhetoric and the reality. They say we have a planet in peril, but the policies are basically business as usual or small perturbations to business as usual. It's what I call greenwash. Because up until the Kyoto Protocol, carbon dioxide emissions were increasing 1.5% per year. Since then, despite the economic downturn of the last 2 years, the emissions have increased 2.5% per year. So rather than decreasing, they're continuing to increase. The problem, the fundamental problem is this. As long as fossil fuels are the cheapest energy, we will keep burning them. That's as certain as the law of gravity. So the solution is you have to put a rising price on carbon so that the clean energies can compete with the fossil fuels. So what I argue is that we need to collect a fee from the fossil fuel companies at the first sale, at the mine, domestic mine, or the port of entry at which the fossil fuels are imported to the country. And all of that money should be given to the public. You divide it equally on a per capita basis among the public. That way, the public would have the money to deal with the increasing energy prices for fossil fuels and begin to move to alternatives. That's a simple, honest way to deal with the matter, and it lets the marketplace decide what are the alternative clean energies that should be supported. And it would stimulate the economy, and it would stimulate innovations. In contrast, cap and trade is a scheme that's designed by big banks and fossil fuel interests to continue basically business as usual and allow the big banks to make a lot of money. There's absolutely no value to the system added by the big banks. We don't need banks involved in this. All we need is to collect the money from the fossil fuel companies, distribute it to the public in a simple per capita basis, and that is the only way that you can get an international agreement, because there is absolutely no way that China and India and developing countries are going to accept a cap on their economy. And why should they? Because their emissions are an order of magnitude smaller on a per capita basis. Their contributions to climate change are very small. The climate change is basically due to emissions from the developed countries. As I mentioned, a fee and green check approach would address the problem and be an internationally viable approach. Now, I want to just say a few words about this intergenerational injustice of climate change. If parents understood this matter, parents have always not only been fair to their children, but even sacrificed for their children. But the parents do not understand the problem. I said there's this gap between what the public understands, because the fossil fuel interests would prefer to continue business as usual. They've managed to keep the public uninformed. Now I have 2 more grandchildren. My son has 2 children. This Jake is 2.5 years old, and he's a gentle giant for his age. He's at the top 1% of the size. According to the charts, he will be 2 meters tall. And he now has a baby sister who is 2.5 days old when I took this photo. And Jake thinks that he can protect his baby sister. But what Jake doesn't know is that if we continue business as usual, the climate system is not going to be under the control of young people. We will have set in motion processes that are not possible to control. So one thing that I've done is we now, a few months ago, we started something called a Million Letter March, where we're trying to get 1 million people to write letters to congressmen to try to make clear that we want the governments to deal with this matter. So Sophie, who's my oldest grandchild, was writing this letter to President Obama, and then she was looking at me when I was reading this letter, and she was quite confident that I was going to like her letter, because one of the things that she wrote in the letter was, "Why don't you listen to my grandfather?" And so then Sophie and Connor and I were celebrating Sophie's good letter. Let me say 2 things which are words of optimism. I just was in China 2 weeks ago, and China to me is a source of optimism, because they are investing tremendously in renewable energies and nuclear power, clean energies that do not produce carbon dioxide. They're now #1 in solar power, wind power, and new development of nuclear power. And they have every reason to want to move away from dirty fossil fuels, because for one thing, they will suffer more from climate change than most countries. They have 300 million people living near sea level. They also have the dirty atmosphere and water from air and water pollution, which they want to clean up. They also they don't want to have the fossil fuel addiction that the United States has. They see all the problems that the United States has in trying to protect supply lines for fossil fuels. And they see that economically they can actually benefit if they develop quickly these clean energies. The other thing is, I think we need to, the legal approach, I think we need to sue our governments to do their job. And I think in the United States, the Declaration of Independence starts out with the phrase, "We hold these truths to be self-evident that all people are created equal." And that's the basis in the Constitution of the United States for the concept of equal protection of the laws. That concept in the 14th Amendment is the basis by which minorities, the courts could help force desegregation. They could tell the government, give us your plan for desegregating schools and other facilities. And the government had to report back as to how they were doing this. In the same way, the government can be, I think, required to reduce its emissions of fossil fuels and to report back to the courts on what it is doing to reduce those emissions. So that's one thing that you can expect to, I think, occur over the next year or two. Attempts to begin to sue the governments to do their job. And the rationale for this is that the executive and legislative branches of the government are, what has become very clear, they're very strongly under the influence of money, which is now playing such a big role. Democracies are not functioning the way they were intended to function, where they were one person, one vote, and for the sake of the public. In fact, money talks in Washington and other capitals. But the judicial branch may be less subject to that influence of fossil fuel industry. So I think there's a better chance that we can get some action from the judicial branch of the government. And so that's what's called atmospheric trust litigation, and you can read about this on my website. Thanks.